Welcome, y'all. Thank you for being here. We're really excited to kick off this session today to talk about phenomena and transfer specifically for the NJSLA-S. We're really excited that you're here, and we're excited to introduce ourselves and then dive into the session. So thank you all for being here. Let's get some introductions out of the way. So hello, my name is Brendan Finch. My pronouns are he, him. You can tweet at me at birdbrainfinch if that's a thing that you like to do, or X at me. That's the verb we use now. I taught middle and high school science for 7 years, but I left the classroom in 2014 to build Rockula.com, which was our first product focused around adaptive reading for science, and then started building InnoOrbit a few years ago to focus around the NGSS and support students and teachers and districts with making sense of sense making, and specifically assessments. I wrote a lot of the assessments of the site to begin with, but now I'm spending a lot of time talking to and doing trainings and working with other curriculum companies or state leaders or district leaders to figure out how we can better support everyone with assessments and with the NGSS in general. So I'm really excited that y'all are here. Thank you so much for taking the time to be here and participate in the chat too. It's wonderful to see people sharing their thoughts and what they do. So I also, just a fun fall fact, is that I believe that salty baked pumpkin seeds are the best part of pumpkin carving. I like art. I like music. I'm a musician. I do not care at all about carving the pumpkin. I just want the pumpkin seeds. I want them salty. I want them baked. I want to eat them all right now. I can feel them in my teeth as I say these things. And this is my wonderful colleague, Andrella.
Hi, everyone. Thank you so much for being here. So my background is in elementary special education. I taught in Brooklyn for 4 years, and I'm super passionate about differentiated instruction and inclusive education. At InnoOrbit, I support districts and leaders with piloting InnoOrbit, getting to know our platform, any questions that you may have. I'd love to support you. And my fall fact, I don't think is showing up for whatever reason, but I'll say it out loud. I recently found out that over 35 million pounds of candy corn are produced each year, which if you lay them flat, then it would create 4 rings around the moon, which I thought was just a crazy fact that every year that's what happens. And
let's go ahead and dive into our session today. Real quick, first, I want to just kind of walk you through what InnoOrbit is. If this is your first time joining us, then welcome, welcome. I see a lot of faces, or a lot of names, not faces, that are familiar. But if you're just here for the first time, I want to just define what we do. So we do 4 things. So the first is that we find phenomena. The goal with the NGSS and prepping for the NJSLA-S is that students should be looking at phenomena they've never seen before and applying their understanding from class to this new thing. So today, our main focus is phenomena and how we can use phenomena throughout the course of units and school years in order to build capacity for students to do this thing, which is learn and then apply that learning to a novel phenomena. And with those phenomena, we write lots of questions. So I think we have nearly 10,000 questions on the site at the time of this recording, and that's really focused on scaffolding up students' ability to make sense of that phenomena. So we have simple questions, 2-dimensional, more complex, and then 3-dimensional, really complex performance tasky type questions. And all of those things are tagged with really, really detailed tags so that we can give you reports that are super duper detailed. So not just students did okay developing using models, or for y'all in New Jersey, they're kind of 3 categories of SEPs. You don't even see individual. It's how do they do on the sense-making practice or the investigating practices or the critiquing practices? And so what we are focusing on is saying, okay, so students did okay developing using models. They did really well using a model to test cause and effect relationships in interactions in a system, but they really struggled to develop a model to describe unobservable mechanisms. And so that things that are at such a great scale, such a small scale, that they're so abstract they can't observe them directly. Those are things that students are struggling with, which is something very specific you can talk about, scaffolding for those astronomical scale or geological time scale things that are just really, really hard to communicate. So that's our goal. And then we also do a lot of professional learning. So we're working with districts almost every day with gathering information and building capacity towards the NGSS. And so if that's something that would be helpful, we do a lot of research on this. We've worked with many, many districts across the country building capacity for teachers and admin on the NGSS. And everything is driven by teacher feedback. So we're really, 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 really into pulling feedback from our teachers and building our sessions to continue. And also, if you're going to be at NJSC, please come by our booth. We would absolutely love to see you next week. If you want to learn more about InOrbit, thank you so much, Julia. My colleague Julia is dropping some links into the chat. You can start a pilot on your own to explore, or you can click on the link in the description of this video, make a meeting with us. And so you can learn more about the platform, and we'd love to talk to you about that. Cool. So now let's dive into our topic for today. So we're talking about phenomena and transfer for the NJSLA-S. We're going to explore some of these test items and then look at some really concrete strategies that we've developed at InOrbit to help students make sense of phenomena through transfer tasking throughout the course of a unit. At first, we're going to be together for about an hour. I'm going to be honest. I think we're actually going to finish in about 45 minutes. So hooray. You're welcome for the extra 15 minutes of time, but we're grateful that you're spending time with us here. So first, we're going to talk about phenomena and sense-making, and we always think it's really important to define what representation is and what sense-making are in the context of actual questions. We'll talk about 3 different criteria for sense-making and for phenomena: that they need to be novel, they should be engaging, and they need to be culturally relevant and accessible to kiddos. And then finally, we're going to dive into the NJSLA-S and some release test items in there. So we'll look at some examples from that, and then also InOrbit's examples. And within this part of the, this is really like the kind of interesting part of our presentation for today. We're going to look at ways that you can use phenomena throughout the course of a unit to help prepare students for those like really gnarly clusters of questions on the NJSLA-S. And then we have some really concrete strategies. And so we kind of give examples of those in the previous section, but then we'll really lay them out explicitly for you, like some pros and some considerations for all of those, for kind of like helping students to prepare to transfer the knowledge to novel phenomena. So let's go. Aaron's excited. I'm excited. Andrilla?
Super excited.
Sweet. All right, good. Okay. Okay. So first off, I want to walk through a little bit of a sense making and talk about phenomena, talk about representation and sense making to kind of like set the stage for our conversation for today. So we always like to do this with a performance expectation in mind. And so let's look at ESS 1.3. So this PE at the middle school level asks students to analyze and interpret data to determine scale properties of objects in the solar system. This is kind of a weird performance expectation. Analyze and interpret data is like what you'd expect. The DCI is just that the solar system contains all of these objects. They're held in place by gravitational pull, but it's not really the objects that we're talking about, the memorization of those, but the scale properties of those objects, which is really, really interesting. And the cross-cutting concept in this case for this standard is actually really at the forefront of what students have to do. So they just need to understand that we can observe things at different scales, and we can maybe use models to like study systems that are too large or too small. But this is one of the only performance expectations that I can think of where like the cross-cutting concept is at the forefront of what students need to do. And so with that, let's dive into our slides and kind of like see what it looks like for students to be making sense of this phenomenon. So I'm going to show you 2 different questions, and I want you to kind of think about the differences and similarities between these questions. So question number 1, we have a list of planets, and we say, put the planets in order from largest to smallest according to diameter. All right. Question number 2, we have this storm data from different planets. And so we have the diameter of the planets, what the planet is, like primarily composed of. Is it a gas, ice, or rock planet? And then also the approximate size of storms on those planets. We ask the question, your classmate Pablo says that Earth has some of the biggest storms for the size of our planet. Explain whether Pablo's claim is correct by using the data in figure A to compare the scale of Earth's storms in relation to Earth's size to the scale of storms on other planets. So we see the scale properties of those planets. Tell me what's the difference between these 2 questions, and why is noticing those differences important for us as educators? So obviously we want students to move towards that second one, but we want to walk you through just some of the differences that we notice between these 2 questions to kind of like scaffold that. So if you were like, I don't really know what the difference is, then allow us to explain to you. So that first one is completing a task that students have more than likely seen before. So just ordinal organization of numbers, biggest to smallest. I actually think like students in lower elementary school could easily complete this, even though it's supposed to be a middle school level question. But these are the questions that we used to ask students prior to the NGSS and the new science test. So students don't have to explain how, they don't have to explain why. There's no complexity involved in this. They're not analyzing anything. They don't have to interpret things. They're just representing their knowledge about the size of planets, the size of numbers. Even the planet thing, those could be like fruits. It like doesn't matter. It's all just ordering numbers. And so this is like an example of a question where students represent an understanding they already have. So we call these questions representation questions. But the other question is different. So this question uses data to explain that DCI, that there's different properties in the solar system, all these different bodies. And the cross-cutting concept is really at the forefront of this, which is scale, proportion, and quantity. So what are the scale properties of those planets? They need to apply those 3 dimensions to this novel thing. So probably students have not compared the size of storms across different planets and using the diameter of those planets. So this is specific and novel. It's a real world thing. We're going to talk much more about what a phenomenon needs to have in order to be a good phenomenon. Students are making sense of that phenomena. They're analyzing and interpreting that data to make sense of it, which is why we call these phenomenal questions. And these are the types of questions we want to build students up to. But the question that we want to consider in our session today is, how do we get students up to that point? So how do we choose good phenomena to allow them to get up to there, up to the point they can answer these questions? And second, so they have practice for it. Second, what does it look like to practice for this? Because that sounds great, Brendan, let's get them up here, but how do they practice? And that's what we're going to talk about for the rest of the session today, is how they might practice to get up there. So first, I'm going to kick it over to Ondrilla, and she's going to talk to us a little bit more about what sense making looks like, what phenomena look like, and some criteria that we can use to build and choose phenomena that help to promote sense making. Just showing some cool GIFs, some explodey videos, or something doing some discrepant event, that's great. That might be an example, but we want to find phenomena, which that is a little bit different than just providing an example of something. So I'll pass it over to Andrilla to kind of walk us through some criteria that we can use to evaluate our phenomena.
Thanks, Brendan. So first, phenomena and problems are the most critical predictor of whether a task can give students an opportunity to engage in 3-dimensional performances. So this means that if we have great phenomena, we can ask great, deep 3-dimensional questions. But if our phenomena are flat or only 1-dimensional, we can't ask those complex 3D questions. So it brings us back to that question that we need to keep asking ourselves: how do we ensure we're including engaging, relevant, and compelling scenarios in assessment tasks? So we have a couple criteria that will help us to make sure that we're giving our students the right phenomena, and let's jump right into them. Criteria 1, we have, is it novel? We need to consider, is the situation new to your students and not a scenario they have seen in class before? Also, is the phenomenon based around a specific instance, not a broad topic or generally observed occurrence? So are we talking about water getting hotter, or looking at something specific, like an experiment on how the properties of oobleck change under different forces? Water getting hotter is a generic example that doesn't challenge students with novelty. And the second is a great example of a discrete instance phenomena and a novel phenomena. Like Inspector Clouseau, we want your kids to say they've never seen that stuff in their life. I'm sorry, Brendan, I can't do the accent. All right, let's go into criteria 2. Is it accessible and culturally relevant? What to consider here: is the phenomenon a real-world observation? Are we presenting well-crafted, grade-appropriate data? Is it explainable using grade-appropriate DCIs, SCPs, and cross-cutting concepts? And does it effectively use at least 2 modalities to present this information? I think we can do it. So let's go into criteria 3. Is it engaging? We need to consider, is the phenomenon puzzling or intriguing? Is it sufficiently rich to drive the task at hand by providing students with enough information to engage in sense making? And does it provide a compelling question or observation that needs to be explained? Big picture here, some people will use discrepant phenomena to engage students, where normally they expect something to happen, but then we show them something else. For example, how can a balloon stick to a wall without adhesive? There's nothing sticky on it, but it's sticking. What's going on there? Students will have to use their understanding of static and forces to drive their thinking. We want Mr. Johnson from Abbott Elementary and our kiddos at large to find our science content interesting. So just to review, the 3 different criteria are: Is it novel? Novel phenomena allow us to move students from representing science knowledge towards making sense of new situations. If we're building future scientists, we need to ask them to do more than tell us what they know. They have to be able to apply that knowledge in new ways, and that's what they'll need to do on the NJSLA-S test. Next, is it accessible? Is this appropriate for my students at my grade level where my students live, taking into account their experiences in view? And then, is it a real world example, or did I pull some clip art and make up figures and data to present to my students? Then our third one is it engaging? Is it puzzling where students willing to say, and apply what they already know to figure out what's happening here? And do observations need to be made to make sense of the phenomenon? Can we answer questions by blocking out the phenomena, tables, graphs, and data, or do we need that information to be able to answer those questions? And yeah, that pretty much sums it up. Back to you, Brendan.
Well, thank you, Andrilla, for setting the stage for us, giving us some criteria that we can use to evaluate what a phenomena is. Super, super helpful just to have that context. And so now let's dive into using phenomena we're going to call it test prep, but also just like preparing students for making sense of additional phenomena later on. And they're going to have to do this on the NJSLA-S. And so we're going to use this as, like this very specific context to look at a phenomena and other questions that we could use in phenomena that we could use to build up to that. So this is one of the assessments on the NJSLA-S, which is about this bitter taste gene. So whether or not you can taste this bitter taste. And so we have this like taster versus non-taster. I think there's a gene like this for cilantro, where for some people cilantro tastes like soap, and for others it tastes like a wonderful garnish. I'm definitely in the wonderful garnish side of that. But we give students these alleles, so these individuals. There's these images of chromosomes. They talk a little bit about how the traits of folks and their phenotype and their genotype, and students have to answer questions about this image and this phenomena. And so this is actually coming from the standard MSLS-32. And so this is a really interesting standard. It's a very, very rich standard where students need to develop and use a model to describe why asexual reproduction results in offspring with identical genetic information and sexual reproduction results in offspring with genetic variation. This is important because what we're looking at in that NJSLA-S phenomena is sexual variation. We have two pairs of chromosomes that we're looking at, and we're looking at what those offspring might look like, and like the probability of having the bitter taster or non-taster gene be present or be expressed. And then we also have another part of this phenomena that talks about asexual reproduction. So this is actually a really interesting PE because it could be either. So students actually need to be prepared to answer questions for both sexual and asexual reproduction, so identical or non-identical, so where there is some combination of those genes. And so we're going to do that by looking at several different phenomena. So in this standard, there are 3 dimensions always. So developing these models is that first one, so we should have students looking at some model. Those could be Punnett squares. They could be representations of those chromosomes, as we saw in the other one, but that's important. And then there are 3 different DCIs that this standard covers, because there's reproduction, sexual and asexual. There's inheritance of traits, where they need to understand how traits are inherited. And then also there's variation of traits. So because of sexual reproduction and mutations, there can be variation in how traits are either passed down or expressed, and how they're combined in subsequent generations. The cross-cutting concept here is cause and effect. So we should always be looking at a thing and how that cause relates to an effect. And students should be showing that through models or seeing that in models. And that's really, really important. So for this standard, if it's phenomena, let's say we're going to use some of the phenomena on inner orbit, or you're going to pick your own phenomena, and you want students to get lots and lots of experience with this over time. So let me provide you with a roadmap for kind of like breaking down what phenomena might look like in a unit where you're going over this heredity concept. So on our website, a couple of phenomena we might use. Maybe at the beginning of the unit, we talk about how did the Black Death devastate Europe. And this is a asexual reproduction, where we're just looking at this one organism that reproduced itself over and over to an alarming degree of success, and really decimated the population of Europe. I probably shouldn't be smiling about this, but it is an example of asexual reproduction and how those genes can be passed down, and how this organism that resulted in the Black Death, or this plague, was able to reproduce with great efficiency. So that's our first phenomenon. And then maybe in the middle of the unit, we're going to have another phenomenon that we're going over, which is why do roses come in so many different colors? And so we start out by kicking it off with something dire and asexual, and then we get into something that can be sexual or asexual. So roses can actually reproduce both ways. And that can be like a mid-unit phenomenon. And so this is considering and layering over, just to be clear, maybe we've got an anchoring phenomenon in our unit, and we're going to use these interspersed from that anchoring phenomena to our assessment phenomena that we have at the end, which should be all different. And so ideally, we have many different phenomena that we're looking at through the course of that unit. And these are a couple from the InOrbit website that you could use to kind of like show students how this one concept looks, that organisms pass their traits, their genes on, those result in traits, and it differs with sexual and asexual reproduction. Okay, and maybe at the end of the unit, you want to use a different phenomena. So we have this like, how can such different squirrels be siblings? We have these different squirrels. They look very different, but they are siblings. And it's all about, the expression of genes and what is passed down to them. Okay, so let's just say we have that phenomena that we used for that standard, that middle school life science standard. But maybe you're like, hey, Brendan, my students are starting at a level where they need even more phenomena and they need lower level phenomena in order to access those more rigorous things. Well, we got something for that. So what we recommend you do is you go from that middle school life science performance expectation and you walk back to the prior knowledge, so the prior grade level standard for your kiddos. And in this case, we walk from that NJSLA-S standard to 3LS31. And so this focuses on students analyzing and interpreting data to provide evidence that plants and animals have traits inherited from parents, and that variation of those traits exists in a group of similar organisms. And so looking at a large population of organisms and seeing how the inherited traits from the parent generation changes, and we see differences in the offspring generation there. So students have to analyze and interpret data in this third grade standard. They need to look at inheritance of traits and variation of those traits, and then they look at patterns. So you can very easily see how this standard feeds up into students' ability at that middle school level. And now let's just say we want to use this as like a starting point for our analysis of phenomena and introduction of phenomena. And so maybe we can go back to some of these, phenomena that we have from third grade. And so we actually have 3 different phenomena on the InOrbit website as well. And you could probably these are easy enough phenomena to come up with where you can, build these on your own. But first we can say, how can the same type of flower look so different? So maybe we're going to project this up on the board or ask students, say hey, how can this same, how can I plant these flowers in my garden? And that same type of flower can have all of these different appearances. Why is that? Or how do tigers get their stripes? How do offspring of tigers get their stripes? And so we can just look at how there are differences in offspring of tigers and how we see the traits expressed in different ways. There's albino tigers here. There are non-albino tigers here. Super interesting. And then also looking at a phenomena like, why is this horse so small? These are all different phenomena we have on our site, which use that same concepts of variation of traits and inheritance of traits. And maybe we can give students examples at a lower grade level, so from middle school, and go down to that third grade standard and say hey, look at these phenomena too, and make sense of them. So we can project them up on the board, but I'm going to give you a couple of examples of different ways that we could use those phenomena in our classroom and some concrete structures to say hey, look, we have an anchoring phenomena we're using in our unit, hopefully. And then we have a phenomena that we're going to use in our assessment. The NJSLA-S is one example, but InOrbit has lots of these, obviously. That's what we do. But maybe we can use these phenomena throughout the unit as well to kind of prepare and give students practice before that final performance. And so some examples of what you can do with this are, let's just take that Black Death devastation phenomena. And so we're looking at, this bacteria and how it reproduces over time. And so we've got this model for students. Then we can also look at this diagram to show how that bacteria changed over time through mutations and by evolution. Super, super interesting. And we can use this at the beginning of our unit. Let's say we're starting this unit on variation and heredity, and we want to give students a phenomena exploration in class. This is going to be a whole class walkthrough and discussion. So I'm just going to project this up on the board and say, hey, we talked about, that roses or flowers can look different in a group of flowers, but it's the same flower, but they all look different. So what is happening with this bacteria? How do these bacteria change? Are these bacteria all the same, and what's happening over time? And then the teacher can have students contribute their understanding of the DCI. So, what do you see happening from bacteria generation 1 to 2 to 3 to 4? And like, what does that mean for both the scope of this bacteria and also the traits that they're passing down? So you as the teacher can really you can feed a lot of the discussion, but then pull out, maybe they have some understanding of inheritance and of variation. And then you could also include some discussion questions. You can use the questions from inner orbit and ask those, or just ask questions like, what patterns do you see here? What cause leads to this effect? And so, what happens if some of these bacteria, like there's a mutation and then there's a trait that's being passed down that, leads to like, it takes less time for them to reproduce, or they're more immune to whatever this is, or maybe they can survive well on rats or fleas that survive on rats. And that enables them like this mechanism for distribution that is just like unparalleled. And so you can give a lot of these questions to kiddos just verbally. So this is just like a real simple verbal discussion. So let's just say you give that phenomenon in the beginning of your unit, and now we're going to talk about roses and thorns. I'm not going to like sing the seal song, but suffice it to say that we want to give students another example of a phenomena. And so this uses that, more sexual reproduction Punnett squares, which is also what we kind of see in the NJSLA-S question. And maybe mid-unit, we use this as like a printed and scaffolded group phenomena exploration. So we're not going to give a formal assessment with the in-orbit phenomena, and we're not just going to like project it up on the board and say, discuss. But instead, we're going to print this out. And so this is a way where the whole class can like walk through the phenomena. So you can still project it up on the board or have the like dot chem up and walk through. Okay, so what are these roses? What similarities do you see here? What differences do you see here? What could have caused that? You can have those conversations. You can walk through the text of the phenomena as well and see like what students already understand. And then maybe even review the Punnett square down here, this is where my eye goes, because there's, this is a very specific skill. You want to make sure students are ready to do this. But you can let so as a teacher, you can guide them through this, and then let students like, go off in groups. You can prep students with some of those DCI concepts to scaffold, and then allow students in their groups to answer rigorous questions, asking about the cause and effect relationships between these different traits and this mechanism of reproduction, and also look at how those traits are passed down and how they vary. And you can get into the concept of alleles and dominant and recessive and the expression and probability and stuff like that we can see from this Punnett square. So that's one of the ways that you can use a phenomenon in the middle of a unit. So to teach this concept of variation. And let's say we've gone through more instruction. All right. We're getting ready for it at the end of the unit, and we can look at this. How can these different squirrels be siblings? This is again another sexual reproduction example where students are looking at this wild type morph, this brown coat, this melanistic morph, and seeing how all of these squirrels can be, siblings, but look so different. And so at the end of the unit, ideally, because we want to prep them for that NJSLA-S test, we want to give them an individual assessment. So I'd recommend you could use inner orbit for this. We have many, many, many questions on this topic, but build a short online assessment to be administered individually. You can scaffold up your questions, kind of like you did with the conversational questions or group printed phenomena questions. And then at the end of this assessment, you need to have rigorous sense-making questions. We want them to be answering and looking at phenomena that is complex as that NJSLA-S phenomena that we saw earlier. And so this is one of those things where the teachers can scaffold, like you can talk to students and write some stuff up on the board to help them out or walk through the phenomena initially, but we want them to be moving towards independence and removing the scaffolds that we put into place earlier, from the discussion to the printed group work to like this final thing, to this final individual assessment, is necessary for building independence. And we want students to be more confident in approaching these on the NJSLA-S, and then also like in life in general. Okay, cool. So to review, ways that you can use phenomena for test prep and big ideas here. Practice makes perfect. So phenomena should be used throughout a unit to prep for state tests. And so if in every unit, like let's just say this one standard, we use these 6 phenomena from the in-orbit database of phenomena. I mean, those kids have just gone through so many opportunities to apply their understanding of variation and inheritance of traits to novel phenomena. And that means if we did that times, like the 25 standards that we go over in middle school life science, and then get to the end of your test, I mean, those kids are going to have gone through hundreds of phenomena throughout the course of that one year. And if it's, in 5th grade or 8th grade where they're going through that test, or if you're building capacity from 6th to 7th up to that 8th, or from 3rd to 4th up to that 5th test, they're going to be very well prepared for that. So use those phenomena as ways to model and practice transferring knowledge and sense making. So you as the teacher, you understand how to do this, but you need to explicitly show students how the things that we talked about last time apply to this new thing. And the more you do that, the more prepared they'll be to work in groups to do that and then individually be able to answer questions like that. Lower the stakes with a prior grade level. So if your students are, like if you anticipate that they're going to struggle with this, which we work with schools across the country and the world that are implementing these standards, and always there are gaps in knowledge and always there are gaps in skills. It is really, really hard to make this a new phenomenon. So you want to give them lots of opportunities to do this by lowering the stakes. So ask some of those third grade questions to prep the kids for those middle school questions that can lower the stakes around making sense of phenomena and give them more confidence and more lower pressure opportunities to do that thing, which is a hard thing. All right, great. So that's it. Now I want to walk you through some of those strategies without the phenomena to kind of walk through some of the pros and some considerations with that. And first, I'm going to pass it over to Andrilla to walk us through some of these strategies for using phenomena in your classroom to prep for the NJSLA-S and beyond. To you, Andrilla.
Thanks, Brendan. All right, to start off with, you can lead a whole group discussion. This is a super informal approach with verbal questioning where you would project the phenomena up on a board with 1 to 3 verbal discussion questions. You will then, as the teacher, lead the discussion by asking probing questions. Some pros here: the strategy is super scaffolded and teacher directed. You'll be providing space for students to access prior knowledge in a low stakes context. And you'll have the opportunity to model sense making to students. Some things to consider: misconceptions may surface, and this approach doesn't hold individual students accountable in a meaningful way. But hey, engage in your inner Oprah and let's have those talks. And then the next strategy is that you can assign some printed group work. The stakes are lower here and there's more formal questioning. Here you would choose a phenomena with 5 assessment questions and then have students use their printed sheets with the phenomena and go through. Some pros here are that this is great for working up to independent analysis. It provides flexibility for students to write on paper and take a break from technology. Students will also have the chance to explain their reasoning to their classmates and go through the process of sense making together. Some things to consider here are that this strategy is best implemented near the middle of a unit so that we're fostering idea sharing and collaboration. We also recommend having a whole group debrief afterward, so hopefully your class looks more engaging and collaborative than what's going on here with The Simpsons. Now, Brendan, what are some other strategies that we can share?
That's a good question. And I'm glad you mentioned this GIF. This is not an ideal classroom, in my opinion, in many ways. The Simpsons, funny, not exactly modeling good pedagogy. So another way that you can use this is phenomena transfer stations. This actually came from our work with one of our partner districts in Maryland, where a teacher was doing this thing. So she'd print out 3 to 5 summative assessments, so 3 to 5 different phenomena, and for the same standard. And it would just be like a crazy party day on this one standard for her students. And they would go from station to station and look at different phenomena from the same standard. So a pro is that students keep seeing these same ideas from like different lenses. So you really get to see what this is from lots of different scenarios. We want students to have conversations. We want to spark curiosity. So all of the phenomena we looked at here are different ways that traits can be inherited and vary from generation to generation. And so we just want students to think about that. And then they can think about lots of other things. When they're like, oh, here's 6 examples of that. I can probably think of others in my own backyard or my walk to school or from what I see on the bus on the way to school. You can scaffold those questions to support students up to a rigorous sense-making question. So, start with some easy questions and then have some tough ones in there. Some things to consider is that in groups, students can support each other with pre-assigned roles. So if it's like you read the phenomena, you're the recorder, you find the evidence, and then you're the fact checker or some of the timer or something like that. So each student has a role. That's really important. We also recommend that you use this towards the end of a unit. So students need to have a little bit of preparation before they're ready to put their hands all together. I think, is that a dog or a cat? Anyways, and I recommend, especially with things like this, you have a whole class debrief afterwards. So you talk about how to make sense of the phenomena, make sure to address any misconceptions that came up. And 90% sure it's a cat. Yeah, I don't know. It's like fake though, so it could be either. Anyways, so have a whole class debrief afterwards to make sure that you model for students again how they're supposed to make sense of this phenomenon. All right, so at the end of a unit or of a course of study or a single standard lesson sequence that you're going through, have a single phenomena, ask rigorous questions. This is what they have to do for the NJSLA-S, and we want to prep them for this by giving them practice on this. So you can choose 2- and 3-dimensional questions for the same standard for formal online assessment. We want students to get practice with computer-based testing. And we also want to gather deep data. So if you're using InnoOrbit or something else that has like some really, really beautiful reports, I'm partial to our reports, obviously, but that's going to help you to gather some data on where teachers need the most support, or students need the most support, or you as a teacher, I guess, both. And it's also an opportunity for students to independently make sense of phenomena. Some considerations are that it's less scaffolded, and some students may genuinely struggle. I'm sure if you've given your kiddos these like really rigorous assessments, it's very hard, and they're genuinely going to struggle with them, which is okay, and it's kind of important. It's best done towards the end of a unit or of some learning sequence. And you might not want to debrief afterwards, or there's going to be some kid who's like really stoked to like share their answers with their peers. And that might not be the most secure thing. So maybe not a debrief thing, unless it's the culture at your school or district that you debrief after those assessments. Cool. And let's wrap it up and kind of summarize what we talked about today. So main takeaways from today's session are that there need to be strong connections between phenomena and the 3 dimensions. So super important that you're using those 3 dimensions in your phenomena. Phenomena have to be novel, engaging, and relevant, culturally relevant for your students. Are they important? Are they interesting to them? This is crucial. Then we also recommend that phenomena challenge students to grapple with uncertainty while staying within their ZBD. So we want them to productively struggle, but still struggle. That's like really, really, really important. And then getting students to engage with phenomena throughout a unit or the school year will build up what they need to do on the state test. And that's super important that they're slowly building up to that. And we give them lots and lots of practice. Cool. And that concludes our session for today. So we did a lot talking about phenomena and sense making, some criteria for that. We talked about the NJSLA-S, went through an example of that assessment and one of the phenomena in that assessment, and some InnoOrbit examples. So we had 6 examples for that same phenomenon. And then some strategies that you can use for this. So we did it, Joe. Love it. Yeah. So if you do want to chat with us and find a time to pilot, and you want to try InnoOrbit out and use all of the things we just went over in your own classroom, school, or district, we're going to drop a link to our calendar in the chat. You can find a time to chat with us. We also have an exit survey that we're going to drop in that chat too. If you have feedback for us, we would love to see how we can do this better over time. And you can follow us on social. So on X, which we are like formally understanding that it's not called Twitter anymore, so it's called X. So you can X at us at InOrbit.edu. Also, Instagram and Facebook are good ways to find us and learn more about what we're doing. And subscribe to our YouTube channel. So we're constantly putting out YouTube videos. This will be on YouTube as well. So let us know about that, or send us an email and let us know how it can be helpful. But we'll hang out for questions for a little bit. If you also have questions and you're watching a recording of this, go ahead and leave those in the comments and we'll get back to you as soon as possible. But thank you all very, very much for being here, for walking through these different examples of how we can use phenomena for students to transfer and build up to this state test. We really, really appreciate you being here. Thanks, everybody.